Is this thing on? Okay. Hi, I'm Anderson, just Anderson, and I'm here to show you how to calculate a couple of easy problems dealing with the forces of gravitation, which is in a certain chapter in the physics book, and it's about Christmas time, as you can tell. With my famous battle cry, bah humbug, let's get started. The gravitational attraction between a 20 kilogram bowling ball and a marble is 1.48 times 10 to the minus 9 newtons. They are separated center to center by 30 centimeters. What is the mass of the marble? Now we're given some information here. Okay, mass is 20 kilograms, so that's our object of mass 1. Our force due to gravitational attraction is 1.48 times 10 to the minus 9 newtons, which is not much, but these gravitational forces aren't going to be large by any stretch of the imagination. The radius is 30 centimeters, which we change to meters because that's how we operate around here. And then the gravitational constant G is 6.67 times 10 to the minus 11th newtons times meters squared times kilograms squared. Now, why the meters squared and the kilograms squared? Because they cancel out units so that we are ultimately left with kilograms. That's the idea. So, what's our formula? Well, our force due to gravitational is equal to the gravitational constant multiplied by the mass, in this case of our bowling ball, times the mass of our marble divided by the radius squared between them center to center. So we wrote out the formula for it. Now we just need to plug in, our values. So our f of g is equal to 6.67, and I'm going to go e to the minus 11th instead of writing times 10 to the, okay, so we're going to multiply that. And then we're going to go ahead and we're going to multiply. We have 20 kilograms here multiplied by x kilograms because that's the mass we're trying to find for our marble. Okay, and we're going to divide that by r squared, or 0.3, and we're going to square that. So this is how we set up the problem. Now we need to get x by itself. We can do that. Okay, so we've got everything all set in. So let's go ahead and let's divide this out first, multiply and divide it. So this is going to be 0.3 squared. That's 0.3 times 0.3, that gives us 0.09. Okay, so that's going to be 0.09 on the bottom, and we have 20 times x over 0.09, and we're going to take that and multiply that by 6.67 e to the minus 11, and that's going to equal, well, they gave us the force of gravitation, didn't they? Absolutely, right up here, 1.48 times 10 to the minus 9th. So we're going to go and enter that here, 1.48 e to the minus 9th. So this is what we have. Okay, this didn't turn out so well on the erase, so let's see if I can redo that. Okay, so with that, and then there we go. So that's what it looks like. That's where our problem is. This is 1.48 here, and now we're going to go ahead and we're going to take 20x divided by 0.09. So 20 divided by 0.09, and we walk away inside here with 222.2 times x, because that's our kilograms for our marble, multiplied by 6.67 e to the minus 11 is equal to 1.48 e to the minus 9th. So this is where we are going with it. So let's go ahead and we're going to multiply this with this, okay? So times 6.67 to the minus 11th, And we are going to get a small number for that. So our small number in this case, now that we're multiplying all this, we're going to get 1.48 e to the minus 8th x. And that's going to equal 1.48 e to the minus 9th. Okay? So we took this, multiplied it together. This is what we got. We still have our x because that's what we're trying to solve for. And here we have 1.48 e to the minus 9th. So now what we can do, we're going to take both sides and we're going to divide it, both sides by 1.48 e to the minus 8th. So when we do that, okay, we are going to get, let's see now, 1.48 e to the minus 9th divided by 1.48 e to the minus 8th, and we walk away with 0.1 is equal to, well, these are going to divide each other out, right? So that's going to be x. So the mass of our marble is 0.1 kilogram. And that, guys, is looking at the whole thing. We looked at our formula. We plugged in the variables we knew. I did not plug this one in quite yet. Okay, I plugged it in here so you guys can see where the numbers are going. Multiplied, divided this out to get this. Then we multiplied it by this, okay, to get this, which is equal to the 1.48 e to the minus 9. We divided both sides by this to cancel it out, so we have x by itself. And here we go, 0.1 is equal to x. Our mass of our marble is 0.1 kilogram, which is still pretty heavy. Okay, we're going to take a look at another one here. So we're going to look at this one here. So two students are sitting 1.5 meters apart, 1.5 meters apart. One student has a mass of 70 kilograms, the other has a mass of 52 kilograms. What is the gravitation force between them? Well, let's see. We've got a 70 kilogram, we have a 52 kilogram. So I have a mass, and I have another mass here. Okay, so we're going to say mass 1 and mass 2, just to keep it simple. We also have a radius, don't we? That is our radius. Now, the gravitational force we need to find, but we do have the gravitation constant, which is what we have here. So we're going to use the same exact formula here that we have, where our force due to gravitation is equal to our constant, gravitation constant, times the mass of the two objects divided by the radius squared between the two objects center to center. So I went ahead and I plugged in the numbers here into the formula. Okay? So ultimately what I did, I multiplied this, divided it out, and this is what I got here. And then I multiplied it times our gravitational constant, and I walk away with 1.08 e to the minus 7, or 1.08 times 10 to the minus 7th. Okay, so we worked through two problems dealing with the universal gravitation, universal law of gravitation. Remember, all objects that have mass are going to put out some kind of gravity force. The more mass of the object, the more gravity it's going to put out. However, you also have to look at how far apart are the objects between each other, because the farther apart they are, the less gravitational attraction that there is between them. If they're closer, there's more gravity, more of a gravitational attraction between them. All right, that takes care of this video, ladies and gentlemen, and just want to let you know, I'm Anderson and you're not. Take care and God bless.